Hi everyone, welcome back. So in the last lecture, we looked at spherical wave expansions, multiple representations, and superdirective antennas. Today, we're going to continue on spherical wave expansions and discuss scattering from spheres. Okay, so we're going to discuss plane wave scattering from spheres. Okay. So there are very few scattering problems for which you can analytically find the solution. So when you can't do it analytically, then you have to do it computationally or numerically. And we discussed a couple of computational techniques in the class before. One of them is method of moments, which is very popular for a few different types of scattering problems. We also discussed physical optics and geometrical optics in the context of reflector antennas, but they can also be used for scattering problems. And of course, there's also finite element, right? So today we'll discuss an analytical case where you can actually solve the scattering problem analytically. And we'll see that there are some very nice results that explain a lot of nice physical phenomena in nature, right? So one of the things that we'll see later is the color of the sky. Why is it blue? Why is it, orange during sunsets? Why are clouds white? And so on and so forth, right? So all of that really comes from a simple expression which we'll derive at the very end. But it essentially comes from the scattering theory of plane wave scattering from spheres. Okay, so let's get into the weeds. We have an scattering problem whose geometry is like this. So we have X, Y, and this should be Y rather. And we'll call this Z. And we have this sphere here, centered at this coordinate system. And we have a plane wave coming in from bottom along K hat. K hat is along Z. And then we orient the coordinate system rather, without loss of generality, such that H is along Y and E is along X. Okay, so that's kind of the problem setup. And we want to see how does this actually scatter, right? So analytically, so we can express the incident electric field equation form as E naught X hat E to the IKZ, and H incident would be E naught over eta Y hat E to the IKZ. K dot R, and K only has a Z component, so it becomes E to the IKZ. And that's from the plane wave stuff we've done several videos ago. Okay, so now we want to express this incident plane wave in terms of a spherical coordinate system, right? So we want to see in spherical coordinates, what does the incident plane wave look like? So I can express the incident plane wave as ER, R hat plus E theta, theta hat plus E phi, phi hat, right? So from this, I only care about, for now, R component, and I can find that by taking ER incident or E incident dot R hat. That's the definition of the R component. And that turns out to be E naught cosine phi sine theta E to the IKR cosine theta. So I substituted Z equal to R cosine theta, and then I took X hat dot R hat. And R hat is nothing but X cosine X sine theta cosine phi. So when you take the dot product, you get this. You can do the same thing for H, which would be HR component is E naught over eta sine phi over minus IKR d over d theta times E to the IKR cosine theta. Okay. Okay, so now what we want to do is we want to expand this R component in a spherical wave basis, or spherical modes. So we want to expand this part in terms of a spherical wave expansion. Okay, and this is the result That's pretty famous. So it's called the spherical wave expansion of a plane wave. So expanding plane waves, plane wave in spherical mode. Right? Because the spherical basis, a spherical wave expansion is the basis for any field distribution that satisfies wave equation, and so is the plane wave. So they both are bases. So you can transform from one to the other, right? It's just a basis transformation. So e to the ikr cosine theta is given by summation n equal to 0 to infinity, I to the n, 2n plus 1, j sub n, which is the spherical Bessel function, and p sub n, which is the Legendre polynomial. Okay, that's the expansion. If you want to see the derivation, it is in section 8.2.1. If we want to go through the derivation here, we'll just use it. Okay, so I want to basically substitute this in here. And that gives me an expansion of ER and HR in terms of spherical waves. Like ERI is E naught cosine phi over minus I KR square, summation n equal to 1 to infinity, I to the n, 2n plus 1, jn hat KR Pn1 of cosine theta. The reason behind this is d over d theta of Pn is equal to Pn1. Pn0 becomes Pn1. Okay, so let's make sense of this. So we have this expression, right? And substitute that in here, and that gives us this expression, right? And here I have jn hat, and just as a reminder, this term is equal to kr times jn kr, right? So going back, let's account for the different terms, E naught cosine phi, E naught cosine phi. Now if I substitute jn kr, jn kr, then one kr will cancel with one of them here, right? And I have 2n plus 1, I to the n, which came from here. I have my summation, n equal to 0, and here n equal to 1. One mistake, couple of mistakes I need to correct. This should be n equal to 1. And I made a small mistake here. It's not a mistake, rather I forgot to mention that we need to expand not just this part, but this whole thing. Okay, so to do that, I'll erase this. And we can rewrite this as E naught cosine phi over minus IKR d over d theta e to the IKR cosine theta. Right? Because when I take the derivative of this thing, I get the IKR cosine theta, IKR sine theta, IKR comes down, and then you do chain rule, and then you get sine theta, and you have to divide by this so that you get back to this expression. Right? Because cosine theta becomes minus sine theta as well. So that's why you have the minus sign. But basically, this is now what we substitute for this expression. So we put this expression in there, pull the d over d theta in, and when you pull the d over d theta and it applies on this term, then that gives you this term, right? Because d over d theta of p0 is pn1. Okay, so accounting for the terms now, we have minus I, kr square, so we have one kr here, and the other kr from this term, Right? E naught cosine phi is E naught cosine phi. The summation is here. This term comes from here. These terms are related. And the derivative of this gives this. So hopefully you see why we have this expression. You can do the same thing for HR as well, right? Okay. So once you have ER and HR, then we know ER is nothing but minus 1 over I omega mu epsilon times d square over dr square plus k square. AR, where AR is the magnetic vector potential in the spherical gauge. Right? So comparing these two expressions, we can now derive an expression for AR. And that is given by AR is equal to, for the incident field, so this is for the incident field, or this is general, sorry. This is the incident field. Okay, so ARI is equal to E naught over omega cosine phi summation n equal to 1 to infinity I to the n 2n plus 1 over n times n plus 1 jn hat AR Tn1 of cosine theta. Okay. Okay. So you essentially put this in here. You take this derivative plus k square, and that will give you this expression. Okay. So let's see why that is. I don't want to leave it hanging like that. Since I said that we look at properties of the Bessel functions wherever required, right? So one of the properties is VR plus k square jn hat kr is equal to n times n plus 1 over r square jn hat kr. So this is a property that you can derive for Bessel functions. This is Shelkonov Bessel functions, right? So based on this property, you can kind of see that this term here is nothing but this applied to the Shelkonov Bessel function, right? So when I apply this to this expression, this part goes in here and only applies to this, because everything else is constant with respect to r. So that brings this and converts it into this form. Right now, this term, this and this cancel, and you're then left with just I to the n 2n plus 1, which is this I to the n 2n plus 1, the jn factor, which came from this jn, 1 over r square, came from r square, that's there. And this omega gets multiplied with this term, becomes omega square mu epsilon, which is nothing but k square. So you get this k square out there, minus I, it's minus I, and that's it, right? This term is this term. So again, all the terms are kind of accounted for. Okay? All right, so now we have this nice expression for AI. And a very similar expression exists for AMR, which is the magnetic vector potential, electric vector potential under the spherical gauge, E naught over omega eta, sine phi, summation n equal to 1 to infinity, I to the n 2n plus 1, divided by n times n plus 1, jn hat kr, Pn1 of cosine theta. Okay, so now we essentially have the incident magnetic vector potential in terms of our spherical wave functions. And we want to find the scattered potential because you want the scattered field eventually. So what's the idea here, right? So this is the fundamental idea. So the idea here is from the fact that the key step rather comes from the fact that spherical wave functions are orthogonal. Functions are orthogonal. Okay, which means that if I have a given spherical wave function, so if I have, let's call this, I don't know, SWE1, right? Or IJ for some index M and N, SWE IJ can only interact with SWE IJ. So if I have an incident field with a certain spherical wave function, because I have spherical symmetry in this problem, it can only excite the same spherical wave function. Okay, so another way to think about it is that I can treat this as my incident wave is coming in as a two-endport network. So I have endports on the left, then endports on the right. It's a linear system. And I have, SWE1, 2, 3, all of these modes. These are all spherical modes. But I can treat them as ports in a linear network. And my outputs are also spherical wave functions. Okay. If I treat it as a system like this, I have incident waves. So this is my incident field, which I've decomposed into spherical wave expansion. And this is my scattered field. Okay. Which I can also decompose into spherical wave expansion. If I do this kind of decomposition, then basically my S parameters will be, or let me just say not S parameters, but the transmission matrix from the input to the output will be diagonal. So this is the transmission matrix, which represents input to the output. So I have my input modes here, and I have my output modes. So this is the input. And this is the matrix. And this matrix will be diagonal. If you choose the same set of modes, of course. Okay, that's what it means for orthogonality to exist, right? Between all of these modes. They can't interact. Unless, of course, you break the spherical symmetry, then they can interact. But in our problem, we do have spherical symmetry, so they don't interact. Okay, because of that, we can essentially expand this scattered field in a very similar form. You can write the scattered field is E0 over omega cosine phi summation n equal to 1 to infinity an hat or an. I don't know what this an value is. hn1 hat ar pn1 cosine theta. So why did I use hn1? Here we saw that we have jn1 or jn for both of them, right? Even this one had jn. The reason this has jn is because here you have essentially a plane wave coming in from minus z towards plus z, a plane wave. So from the origin, this location, it looks like an incoming wave, and out here it looks like an outgoing wave, right? So you have both incoming and outgoing waves. Essentially, you have combination of both. So it's better to use the Bessel function basis of jn, little n. Because in this case, in this basis, if I use this basis of little n has a coefficient that must go to 0. Because the incident wave is defined in free space. Right? Incident wave means there is no scatterer. That's the definition of the incident wave. When there is no scatterer, the origin is included in your domain, which means you can't have the n sub n. Right? That's why you only have an expansion in terms of j sub n. But when we get to the scattered field is the field that is scattered everywhere from the scatterer, right? And those scattering fields are always going out. None of it is going in because it's PEC, nothing goes inside. Because nothing goes inside, it's better to use a basis of outgoing spherical waves. right, which are given by Hn1. We don't have any Hn2 component. If I have a dielectric scatterer, which we'll briefly look at the end, then the scattered field also has an inward going component. So you have to be a bit careful there. But in this case, just using Hn1 is fine. So that's why it's important to kind of understand physically what these different modes represent so that you use the right basis. Okay, this is still an unknown. We need to find what this is. But we have ARS, right? Similarly, there's also AMRS, which would be E naught over omega eta sine phi summation n equal to 1 to infinity b sub n Hn hat 1 kr Pn1 cosine theta. Okay. Okay, so now the next task is to find An and Bn, and we apply boundary conditions to do that. By boundary conditions, find An and Bn. So we've done this 100 times by now, right? So the way to solve scattering problems, whether when we did plane wave scattering from dielectric interfaces, or even when you have like modes that propagate inside a waveguide and you want to find what kind of modes exist, what you do is you find the form of the mode first, and then apply boundary conditions to find the coefficients, how much of each mode is there. That's the standard procedure of scattering problems, or even for waveguides, right? So that's what we're going to do. So what are the boundary conditions? We have two of them. E theta incident plus E theta scattered at r equal to a, which is the radius of the sphere, equal to 0. And also E phi incident plus E phi scattered at r equal to a is also equal to 0. Okay, applying these boundary conditions, you can find A and Bn, which I'll just write out the final expression, n plus 1 over n times n plus 1, Jn hat prime Ka over Hn hat 1 prime Ka. So prime is the derivative, this is the order, this represents the Shelkonov-Bessel function, this is Hankel function, spherical Hankel function of the first kind, order n, and derivative. So there's a lot of notation going on here, but once you understand the notation, it's not too complicated, right? Bn is minus I to the n, 2n plus 1 over n times n plus 1, Jn hat Ka over Hn hat 1 Ka. Okay. So now that we have the coefficients, you have these fields, or rather the potentials, you can go back and find the fields, right? So I'm not going to write out the expressions. They are pretty long. You can look them up in the book. So E, H are now given by, or I should say, can be derived from AR and AMR. These are the scattered fields. And the total field is given by the sum of the incident field and the scattered field. So if you want to look it up, you can look it up in the book. There are equations 8.139, at least in the version that I have here, which is around page 150, page 549. They're very long. I won't write it out. Okay, so we have the scattered field, and it's fairly complicated, long expressions and so on. We want to simplify it a little bit, right? So we want to look at the far field approximation. So in the far field, what do they look like? So we can use the large argument expansions for the Hankel function, the Bessel function, and so on. So as you can guess, the Hankel function looks like an exponential. It's minus I to the n e to the ikr. Okay, so under these approximations, scattered field takes this form: cosine phi e to the ikr over kr summation n equal to 1 to infinity minus I to the n an sine theta pn1 prime cosine theta minus bn pn1 cosine theta over sine theta. Again, the scattered field for the phi component comes minus I e naught sine phi e to the ikr over kr summation n equal to 1 to infinity minus I to the n an pn1 cosine theta over sine theta minus bn sine theta pn1 prime of cosine theta. Okay, so we have the scattered field. Obviously, in the far field, there is no R component, which we know. And the fact that it should be TEM. Now we can look at some quantities or a specific quantity to kind of get some more intuition towards for what's going on, right? So we'll define what is called the radar cross section or the scattering cross section, sometimes called RCS, which is sigma is a function of theta and phi. This is limit r goes to infinity, 4 pi r square mod e theta square, or I'll just say e scattered square divided by e naught square. So it's not exactly the definition. The definition of the radar cross section is the ratio of the scattered power divided by the incident power density. Okay, we know the incident power density is basically this, and this is kind of related to the scattered power. So this is an expression you can derive. In our coordinate system, or I should say rather, this RCS, radar cross section, is much more complicated than this really. Okay, so this is what is called the monostatic RCS. So monostatic means I have transmitter and receiver at the same location. And my target is somewhere there. And I'm looking at what the backscatter is. And I calculate the scattered field out here, the receiver, and the incident power density at the scatterer. I take the ratio of the two things and I get this expression. Okay. Of course, it's a function of theta and phi because it depends on where I'm looking for. If I'm looking from here, it's different. If I'm looking from here, it's different. If I'm looking from here, it's different. Okay, there's another quantity called bistatic RCS. This is when the transmitter and receiver are in different locations. So transmitter is there, maybe receiver is out here. Okay. Now this is a function of four angles, right? Theta transmitter, phi transmitter, theta receiver, and phi receiver. Because both of them can have arbitrary angles. So you can scatter like that, or like that, like that, or I can move the receiver around, like that, and so on, right? And it's also polarization dependent. Okay, so you can have something called copole. Copole which we'll discuss what that is. So basically, I send this given polarization. Let's say polarization is V, and I receive the same polarization. So when we discuss polarization, we said that the polarization is defined as something called a Poincare sphere. Right? So if I have my Poincare sphere here, which defines my polarization state, then copole is when both the transmitted and received polarizations are at the same location. Okay, this is for copole. And if I make a copy of this, okay, cross pole is when so I have transmitter and receiver on the opposite sides. So this is the origin. So my receiver is on this side. Then this becomes cross pole, sometimes called X pole. Okay, so I'm sending one polarization and receiving the opposite polarization. Then that becomes the cross pole. Okay, this is in polarization sphere. So of course you can have copole, cross pole for both monostatic and bistatic RCS. Right, so it's kind of a very high dimensional quantity because you have some dimensionality associated with the polarization, some dimensionality associated with the location of the transmitter and the receiver. So this is really four-dimensional, right? This is also in some sense four-dimensional, right? Because this is 2D, this is 2D. Transmitter, I would say rather transmitter is a 2D point in 2D. Receiver is a point in 2D. And then also positions are points in 2D. Now, if you go into the near field, then it becomes even more complicated, right? This becomes 3D, and then this becomes 3D. Then you can't even define a well-defined, you don't even have a well-defined RCS, right? Or you can have some kind of RCS even in the near field. But typically, it's the definition of actual radar cross-section is in the far field. Okay, far field of the scatterer, I should say. So typically, a scatterer has to be small for RCS. Okay, so now that we've kind of seen what RCS is, in our case, we had copole along X direction, right? The polarization, we go back to the beginning. We said that our E field is oriented along X, right? And now we are interested in the backscatter far field along monostatic or just the monostatic RCS. And we can kind of define E theta to be our copole. Okay, that means E phi would become the cross pole, right? So since we have expressions, now we can actually find what it is. So copole RCS theta and phi becomes lambda square cosine square phi over pi summation n equal to 1 to infinity minus I to the n an sine theta pn1 prime cosine theta minus bn pn1 cosine theta over sine theta square. And the cross pole also has a long expression, which I won't write out. Okay, now what we want to do is we want to look at the copole and cross pole only in the backscatter direction. So I had my sphere. This is the metallic sphere, PEC sphere. Right? I came in from the bottom. I want to see what went back in the same direction. Okay, which means I need to set theta equal to pi, observation direction, and copole would then be phi equal to 0, right? And cross pole would be phi equal to 90. Because we said that E came in along X direction, which means for this direction going back, to have X polarization, you need phi equal to 0. Right? And then the cross pole would be along the y direction polarized. So that's v equal to 90. Okay. So now you can substitute these values in and then take use some of the properties of the Bessel functions, of the Legendre polynomials, and you can show that the RCS is lambda square over 4 pi summation n equal to 1 to infinity I to the n times n plus 1 an minus bn whole square, and the cross pole actually becomes 0, which is very nice, right? And it kind of makes sense because of the symmetry. Okay, so if I go back to my problem, so let's see maybe intuitively why the cross pole is 0. So if I'm looking from down now, okay, so I have my, let's say, x-axis like that, y-axis is like that, hit xy. So I'm looking from down. So I have a plane wave. Plane wave is it's kind of uniform, right? And the polarization is along this direction, coming in like this, right? So there is some symmetry in this problem with respect to the y-axis, right? Any point here and any point here, we see the same field because the polarization is oriented like this. And even the scatterer looks identical with respect to the y-axis has symmetry, right? Which means the scattered field should also have some kind of symmetry because the incident field has symmetry in y, reflection symmetry in y, the scatterer has reflection symmetry in y, which means the current also should have some kind of reflection symmetry. So the current's flowing that way there should flow like this here. I'm just drawing an example. This may not be what the actual scattered currents look like. Maybe it's something like this. Whatever the current is on top, it should be the same on the bottom. Because of that, the scattered field, whatever component was along x, along plus y, you'll have the opposite component. Right? So along the y component of the scattered field will have mirror symmetry as well. Because of that, in the far field, they would cancel along the backscatter direction. So along the negative z direction, this current and this current cancel. There's a null, right? Only these currents add up. Right? So essentially, in the backscatter direction, you can't have a y component when you come in with an x component because of the symmetry in this sphere. That is also true for any scatterer that has this kind of reflection symmetry. Okay, so we've shown it for this analytically for the sphere, but it's also true from this intuitive argument for any scatterer. That's only true, of course, in the backscatter direction of minus z. If you change to some other point, that's not true. Okay. Okay. So now we have expressions for A and B. We can substitute them in, use a whole bunch of properties for uh, the Bessel functions, the Wronskian relation. We can use that relation. We can reduce this quite a bit more. Okay, so reducing it after a few steps and using some large argument expansions, we get actually a nice relationship. Actually, I should say it's not just the Wronskian. So we also want to use a low frequency approximation. So let me actually erase this. So we want to use a low frequency approximation, which means that the size of the sphere is much less than the wavelength. So typically, you expect A to be less than 0.1 lambda, at least. Okay, so under this approximation, you can take some small value approximation to the Hankel functions. And finally, you can show that the cross section in low frequency copole is 9 lambda square over 4 pi times Ka to the 6th. Okay. This is a very interesting result because this says that my radar cross-section or scattering cross-section is proportional to 1 over lambda to the fourth. Right? Because this one is nothing but 2 pi over lambda. So you have lambda to the sixth and then lambda squared. So you get 1 over lambda to the fourth. Okay. So if I actually, now we can also take the high frequency approximation. So this is low frequency. High frequency approximation. So when A is much larger than lambda, then we know that under high frequency approximation, you can use physical optics, which is what we derived many lectures ago. We said that the curvature is much larger than the wavelength, you can use physical optics. Right? So I have my sphere. Basically, my incident current, incident field comes in. Let's say this is the positive z direction. Now I have an incident field. It's coming in like that. That's the plane wave. And physical optics says that essentially the plane wave illuminates this left half sphere. And then there are some currents in this left half sphere. And these currents radiate out. Right? That radiation, the current in the left half sphere is given by 2 times n hat cross h incident. And that was a physical optics approximation. Okay. So actually under the physical optics approximation, the radar cross section looks exactly like the actual area that you see when you look from here. And because this thing is so big, it basically is dominated by physical optics. So you have some radiation going this way from this point. And if you look from very far away, you'll actually see physically the size of this reflector, this sphere. That's the reason actually that even for your eyes, even when you look at an object, the object looks the same size that it physically is because your eyes are actually looking at objects in the physical optics limit, right? And that's the reason that when you touch something, it's the same size as what you see. Luckily for us, we are in the physical optics limit, right? Okay, so if you put these kind of two facts together, what do we have? Like we have a plot that looks something like this. We have our one axis, I'll draw A over lambda, and the other axis is the RCS normalized by the physical size, physical aperture. Okay, now our low frequency approximation said that this goes as, so this is maybe, I'll say this is a log scale, and this is a linear scale. Okay, so low frequency approximation, something like that. Yeah, it changes very fast with respect to wavelength. Okay, so this is basically, let me actually do that in a different color. So when the wavelength is large, you're kind of in this regime. The wavelength is small, you're kind of maybe in that regime, that end, right? So this is more like red. Maybe out here is blue, but different colors. And we know in high frequency, this becomes equal to 1. So let's say this is 1, then comes equal to 1, right, at high frequencies. So of course, this low frequency approximation breaks down at some point, and you would expect that maybe this goes asymptotically like that, there. But in reality, actually, you can show from the full wave solution, if you plot it, this looks something like this. Starts here, and then it oscillates asymptotically to that point. Okay, so this is called the me solution. This low frequency approximation is called the Rayleigh approximation. And these oscillations are called creeping wave oscillations. We'll see what that is. And this is the full solution is called the me solution. I should maybe use a different color. So this high frequency limit is called physical optics. It is physical optics. And so this kind of puts a lot of things into perspective. We have kind of this Rayleigh limit. I should actually put the red on top because that's the final exact solution. Okay. All right. So we kind of understand what's going on here. We understand maybe what's going on here, but what is this going on here? So we'll discuss that in a second. But before that, we want to actually see that this Rayleigh limit or this Rayleigh relationship that we derived here can explain actually a lot of phenomena in nature. So one of the phenomena it explains is the color of the sky. So let me do that here. So if I have the Earth, which is something like that, and I have an atmosphere around the Earth, something like that. So when the sun is above, sun is out here, the light's going through a thin layer of atmosphere. Right? Whereas when the sun is out here, it's going through a thick layer of atmosphere. Right? So when the sun is right above you, what happens is that blue light gets scattered a lot more because of this strong dependence on wavelength. So blue light has a much smaller wavelength compared to red light. So the scattering cross-section looks very large. So the probability of scattering for different photons is very high. Okay, another way to think about it is that blue light gets scattered more from wave theory. So we don't have to deal with any photons, right? So because the radar cross-section of these particles in the atmosphere, which are much, much smaller than the wavelength, which is nitrogen and oxygen molecules. So you can apply the Rayleigh limit. They are very small compared to the wavelength, so they scatter blue light very strongly compared to red light. Because they scatter it very strongly, everywhere you look in the sky, you're looking at scattered photons or scattered waves that have been scattered by all these particles and they're reaching your eye. Right? So if I have the sun is over there and it's producing some kind of beam, have your atmosphere, right? All of this scatters out this way, everywhere, right, from a single point. This also scatters everywhere. Blue light gets scattered. And what you see from your eye here is then uh, if you look in this direction, you'll see blue. And if you look in this direction, you will see almost white, right? Reddish white. Of course, you should not look at the sun directly, but if you look directly, oops. Of course, should not look directly at the sun, but if you look at the sun, it'll look white, reddish white. The reason it looks reddish white is because the light that was coming in this direction, some of the blue got scattered away, some of it got scattered towards your eyes, but most of the other colors went straight into your eye and probably caused some damage, but also looked white. Right? But if you look somewhere else in the sky, then mostly the blue light got scattered from these light rays, and you're seeing it to be blue. Okay? What about sunsets? Right, so during sunset, you have your eye out here. It's not a very nice eye, I guess. Something like that, let's say. Something like that. And the sun is somewhere out there. And the sunlight is coming this way. Now there's a very thick layer of atmosphere that it has to go through. Right? So a lot of the blue light actually gets scattered away in different directions. Same reason again. right? Blue light is getting scattered away, whereas orange and red light is kind of going through, not getting scattered much, right? So it looks kind of reddish. Now, if you look around the sun, if I look at some point out here, that also looks red. Right? This also looks red. The reason behind that is that since the atmosphere is so thick, the probability of scattering for blue is very high, as we saw from the Rayleigh limit. So blue gets scattered many, many times, not just once, right? So the probability of blue getting scattered is higher and higher, whereas the probability of red getting scattered is a little lower, quite a bit lower, because of the lambda to the 4 dependence. Right? And at every scattering, the decay in amplitude for the waves is actually higher. So when it gets scattered more and more, the decay as a function of distance becomes larger and larger. Okay, so for example, if you just take a simple example, so let me actually erase this as well. So if I have some scatterer that scatters some waves, this scattering is at 1 over r square dependence, right? That's the power that's being scattered. At a distance of, let's say, r1 plus r2, this one's power becomes 1 over r1 plus r2 square. Okay, but now if I place another scatterer here, right, then these waves reach this scatterer. Then again from here they got scattered out. Right? So if it goes through two scatterings, then by the time the field reaches here, it would be 1 over r1 square times 1 over r2 square. Right? Because by the time this reached here, it became 1 over r1 square. And then from here again, it got distributed spherically over a surface. So by the time that reached there, it would be 1 over r1 square times 1 over r2 square. Whereas the original radiation that reached here was just 1 over r1 square plus r2 square. Okay, so subsequent scattering always will lead to higher decays as a function of distance. Right, so going back to our picture with the large atmosphere, since blue light went through a lot of scattering events rather, decays much faster and basically gets spread out a lot more than red light. So since blue light got spread out, you're left with basically red light. And that's why sunsets look red. Okay. This is also the reason actually why repeaters or Wi-Fi repeaters don't work that well, right? Beyond a certain distance. Because if I had a source, by the time I got to this point, my field dropped to 1 over R1 plus R2. If I want to add a repeater, I need to amplify this to such an extent that this factor, 1 over R1 square times 1 over R2 square, is larger than 1 over R1 plus R2 square. Okay, so from here, as I take this point larger and larger, you have to plot 1 over R1 square times 1 over R2 square versus 1 over R1 square plus, or 1 over R1 plus R2 square. And eventually this will always beat out. And that's why if you want to hit very, very long distances, at very large distance, the original field will always be stronger than the repeater's field. So repeater only works, is only better than the original field at a certain distance. So anyway, so that's just an aside, I guess, but it's the same principle. Okay, so finally we'll discuss this last phenomena of creeping waves. We won't derive it explicitly, but we'll see intuitively what it is. So I go back to my sphere again. Draw that again. Okay, so I have one wave that came in. So this incident field actually generates a surface wave. This surface wave propagates around the sphere, goes around, and then radiates like that. It's not exactly that. So this surface wave, as it's propagating, it keeps radiating in all directions, little by little, losing power, right? And then when it comes back, some of it, of course, gets radiated back. Again, it goes around, goes around, goes around. Every time it makes a circle, it always releases some power back here, right? And based on the size of this, the length that it travels is going to be like 2 pi r. Right? So what comes back here has a phase factor of 2 pi r times k. It's not exactly this, but something like that, right? So if that is in phase with the original reflection, the specular reflection is the main reflection that happens from this point. If it's in phase, then receive power goes up. Whereas if it's out of phase, receive power goes down, right? So essentially you have this kind of interference pattern. Here they're in phase, then at some frequency, a little bit later, different wavelength, they become out of phase, and at slightly different wavelength, they become in phase, then out of phase, and so on. And that's why you see this creeping wave behavior. It's very similar actually to our Fabry-Perot resonance that we saw earlier. Fabry-Perot is also an infinite number of modes adding up and cancelling. We got this interference pattern, right? Now this is kind of a Fabry-Perot version for a metallic sphere. So I have these waves, and of course it doesn't go only in this direction. In this game here, there is a wave going in all directions, right? And they kind of all go around in all directions, this way, this way, this way, and so on. That whole solution eventually converges in time domain once it settles down into steady state. And in steady state, you have some scattering back and scattering in other directions, which is the creeping wave scattering. That adds up with the actual scattering from the specular point and other points from physical optics. All of those basically add up and give you the full solution for the scattering in all directions. Okay, and it also obviously produces an interference pattern because it depends on the size of this thing. So those are called creeping waves. So they exist whenever you have a kind of a round object. So you have a wave coming in, generates the surface wave, and then you have this creeping wave propagation going on. Okay. Okay. So probably this is a good place to stop. One more topic would be dielectric spheres, but it's the same idea. You have to consider fields inside and outside and then apply boundary conditions by expanding them in spherical wave expansions. But you can look that up in the book. You get very similar results. There are few phenomena that are unique to dielectric spheres, so you don't get this kind of nice physical optics result at the end, because obviously you can't use the physical optics we developed for dielectric spheres. In fact, you'll have actually some crazy oscillations even here. Those oscillations correspond to internal resonances of the dielectric, because dielectric has some internal resonances as well, because there is field inside. So those interfere with the specular reflection, and you get large oscillations even out there. Okay, and in fact, those actually are what cause rainbows. But we're not going to discuss that now. But if you're interested, you can look up internal resonances of a sphere, dielectric sphere, and rainbows. And there's a nice geometrical optics picture that derives that, because we know that geometrical optics is kind of a high frequency limit, right, to our typical full wave solution. Okay, so those resonances out there essentially are what cause the rainbows. That's an interesting topic for another time. And there are some nice YouTube videos explaining that already, so I won't go into it. Okay, so I'll stop here. And if you have any questions, you can leave them in the comments below. Thank you.